Exponential functions. We have some applications here. So if you're going to be a scientist, this is something very, very important. Okay? Especially if you're in like, biology. So what happens to a population of anything with unlimited space and resources? Grows and grows and grows. Right, you've probably heard that before. I hope you've studied it in AP Bio. Right? An exponential curve might look something like that, correct? But is that actually what happens?
No.
No, because we live on planet Earth, and the cows eat all the grass and they start to die, right? Or in case of what's happening now, the mountain lions and the bears and the bobcats eat all the deer, and then they start to die, right? So in reality, we have and then a and then a right? Okay, then it keeps going. Some sort of cycle.
Sure.
And sometimes species go extinct. Yeah.
And they come back.
But you're gonna have some what do you call that? Somebody said it. Carrying capacity. Okay. Your species will exceed the environment's ability to support it. Takes a little bit, and then it starts to come down. Okay. So exponentials are somewhat valid, but once you start to reach carrying capacity, you can see that that diverges and the model falls apart, right? We do study this in Calc BC, where we start to account for carrying capacity and stuff like that. And we come up with much better models for population of wildlife if you want to be a biologist or a wildlife biologist. Okay. So there's one example. Your book details bee populations. Do we know what's happening to bee populations right now?
They're declining.
Dwindling.
Rapidly.
Rapidly. Does anybody know why? It's cell phones, man!
Yeah.
It's the radio waves.
All those
It screws with their
chemtrails.
navigation. I don't know. We really don't know why bee populations are declining. Some people think it's pesticides.
As long as the wasp.
A stinging.
But what's that curve going to look like? Okay, bee populations. Yeah, the honeybee. You know, like. Goodness me. The bee populations are looking like this, right? Are they ever going to get to zero?
No.
Probably not.
We won't let that happen.
If they do, guess what?
No more honey.
No more life.
No.
No more life.
Worldwide crop failure because they pollinate plants.
Like 30% of the crop.
No
Like, you never
more.
seen the bee movie?
Very little food.
That's not true. That wouldn't happen.
Very little food. Okay.
Other pollinators.
There are some, you know, wind has some effects on pollination, but bees are the major pollinator. Okay, so this is called exponential
70%.
decay. Right? The black is exponential growth. That is a form we use for exponential equations. Okay. It's exponential because the x is the exponent. A would be like your starting point.
Is that X an exponent?
Okay.
Yes.
And B is your growth rate. Again, and I can just stress this, mathematically this is a really nice model, but nothing in the real world follows it perfectly. Right, so when you're doing math modeling of anything, there's always variation. Growth constant. Okay? So, okay.
We said someone like, when did you publish? Like, are we dying?
Pretty sure every human that's ever lived has experienced death, Wolverine, so yeah.
Yeah. I'm not saying I'm not dying, but.
Let's graph this. Still died.
Just came back to life.
Still died. He still died.
I still was like
Okay, a lot of you are chit-chatting. I feel like I'm in a lake full of murmurs. Stop it. Shh. Thank you. Don't make me get rude to you too. Okay, y equals 2 to the x. Just do a table here. If x is -1, Obed, what's the y value? Try again. If x is -1, try again. 2 to the -1 is, yeah, it's 2 to the -1, so 1 over 2, right? Okay. If x is 0, okay, we just used 2 of our power properties. If x is 1, and if x is 2, if x is 3, okay. What constant are these multiplied by? Times what? Times? Times? Yeah, these are all times 2. You see where that comes from? That's our base. Okay? Right, so, -1/2, 1, 1, 2, 2. Why did I put a dot there? 1, 2, 2, 1, 2, 3, 4, and so on. So we see the general shape of a graph, right? What's the y-intercept? 1. Okay, that's the difference between exponentials and some of our families of functions. The starting point here is 1, right? 1 times 2 to the x. So that's our y-intercept. Okay, now let me throw a wrench in your works. What's y equals 2 to the x minus 3? What are we doing with the original? Down, 1, 2, 3. Okay. Same shape, just down 3 units. This is not the y-intercept though. It's not -3, see? It's -2. It's the start point minus that number. Okay? You okay with that? Can I shift these left or right?
Yes.
How would I do that?
Would you put in front of the 2 or the?
You're going to mess with the x value.
Yes.
Okay, so let's make sure we got y to the 2 to the x plus 1. How am I going to move that? Left 1. So, left 1. Caleb, Frank, there are no gangsters in the hood here. We're in parachute. Okay. All right, so we can still move things around. We still have y-intercepts, et cetera, right? What if I did this? Do you remember what? Oh, that's dumb. Dumb, dumb, dumb. What did the negative times the x do to a parent function.
To turn that around? Or like
Turn it around.
flip it?
Which axis?
Y.
Y-axis, right? So 2 to the negative x is going to look like this. That's where you get exponential decay. Okay? There's another way to get exponential decay. Not a negative base, but it's good. That's a good thought.
Could it be like a fraction?
Would it be an absolute value with a minus in there or something?
No, fractional base. Okay, so what happens to a fraction with an exponent? You get 1/2 and then 1/4 and then 1/8 and then so it gets smaller and smaller and smaller, right?
Yes.
Right, so that and that are the same thing. Why? What is, yeah, that, right? 2 to the x. 2 to the negative x is the same as 1/2 to the x, which is the same as 1/2 to the x.
Yep.
Those are the same. Okay. So recognize decay. Colorado State games. Imagine that. Okay. I'm going to put one more up here, okay? Let's go with
Thank you.
that color. What's the 4 do to that?
Steepens the slope.
No. Good thought, though. I might have said the same thing in your position. What did I tell you this was?
A.
Starting point, right?
Oh,
Oh, so that's
The y-intercept. 1, 2, 3, 4.
Eureka.
Had a revelation. Okay. All right. Any questions? We'll do a little bit of work on real life questions. Do any of you want to be in biology? Any biologists in there? Or wildlife biologists? Any people going into finance, accounting? You use exponentials? Nobody. Okay. Anybody want to be a math teacher? I use exponentials every year. Yeah, you're full of it. We just advise you not to subject yourself to that.
I don't think anybody.
But, okay, 2 words.
Yeah.
Job security. Nobody wants to be a math teacher, so there are lots of
I'll
jobs.
be a math teacher until like.
I'm just gonna whack you with rulers and say.
Then you'd be an elementary teacher.
Yeah, they're right.
Yes.
Would you teach math? Okay.
I'm gonna teach them everything.
I feel like teaching it.
You would be the worst
Yeah.
teacher in the world.
I was John's tutor for a long time. I think I'm gonna
We'll start a.
Yeah, but that's John.
That's due tomorrow.
No.
Let me make sure we covered it all.
Listen, you gave us your son.
Oh, that's not a lot though. It's like 1, 2, 3, 4, 5. It's literally 10 questions.
Well, I gave you one answer. Okay, it's really short. It's all this. This is all it is. Graphing and a couple of explanation things. Okay? No.
I'll be